When you have lines in 2 dimensions, there are 3 possibilities. Here is possibility number 1. They are parallel and they never intersect. So the question is, how could you tell if you had a vector equation of a line that 2 lines were parallel and will never intersect? So what we're going to do is we're going to set up our system of equations to solve like we would normally to find an intersection point. But when you try to solve, what's going to happen is all the variables are going to disappear and you will get a false statement, like 5 is equal to 3, which is false. Okay? So sometimes people say, well, isn't it enough just to notice that they're parallel? But they could be parallel and exactly the same. So these 2 are parallel, and you can tell by the direction vectors, because anytime one's direction vector is a multiple of the other one. So for example, the 6, 4 is just the first one, 3, 2 times 2. These are going to be parallel. But we can't say for sure that they're not exactly the same line or that they're different. And it's not enough to say that they're different because they have a different point, because it might be that that's just another point on the same line. So when we look at the parametric equations here, for one equation we would have 1 plus 3t and y equals 2 plus 2t. And for the second equation you would have x equals 2 plus 6s and y is equal to 3 plus 4s. This makes 2 systems of equations. We know that the x coordinates 1 plus 3t would equal 2 plus 6s. And our y coordinates, if we equate them, that 2 plus 2t equals 3 plus 4s. That creates a system of equations. You could solve that system of equation any way that you want, using matrices, using the mathematics of grade 10, elimination. I would probably look at this one and try to do something with elimination. Can you see that if I take equation, I'll call it 1, and I multiply everything by 2, I would get 2 plus 6t equals 4 plus 12s. And if I took equation 2 and multiplied everything by a negative 3, I would get negative 6 minus 6t equals negative 9 minus 12s. I multiplied by those numbers. Maybe I'll just put it, so I took 2 times by equation 1, and here 3 times by equation 2. Excuse me. I did that so that I could eliminate one of the variables. I was hoping to eliminate the t's. So now when I add those 2 equations together, my t's go away. On this side, I'm just left with 4. But unfortunately, so do my s's. And on the other side, when I add them, I get negative 5. This is not possible. So those 2 lines are parallel and would never intersect. Now, when you were doing grade 10 math, you would have 2 lines. If you changed them both to y equals mx plus b, and they had the same slope, but a different y-intercept, that's how you could tell that they never intersected in grade 10 math. Okay? Never intersect. Are you good? No? Okay. Second possibility. They do cross at a single point. This is called concurrent lines. So how would we show that? Well, same thing. You set up your system of equations with your parametric equations, and you solve, but this time when you solve, it works. And then you can use those values of s and t to find it. So here's our equation. My parametric equations for the first one are minus 3 plus t, and y is equal to 5 plus 2t. My parametric equations for the second one are 4 plus 3s and 3 minus 2s. Putting them together, our first equation then says that minus 3 plus t equals 4 plus 3s, and in the second one's 5 plus 2t is equal to 3 minus 2s. Again, I would call this equation 1 and this equation 2. I like to use elimination in vector parametric equations because everything is already so nicely lined up. I mean, it wouldn't be hard in this one. For example, can you see it's really easy to isolate t in equation 1? So it would not be hard to isolate a variable and use substitution. But since things are lined up, I'm just going to take equation 1 and I'm going to multiply negative 2 times by equation 1. That will give me 6 minus 2t equals negative 8 minus 6s. I'm going to rewrite equation 2, and you can see already that I multiplied equation 1 by negative 2 so that my coefficients in front of t, if I add them, will cancel out. So now when I add the two equations, 6 plus 5, that's equal to 11. The t's cancel out. Negative 8 plus 3 is negative 5, and negative 6 plus negative 2 is negative 8s. So I have 16 equal negative 8s, and s is equal to negative 2. If s is equal to negative 2, you can go back and use either equation 1 or equation 2 and plug in s is equal to negative 2. So if I use equation 2, I would have 5 plus 2t is equal to 3. If I plug in minus 2, I get plus 4. Now solving for this, 2t equals 2, and t is equal to 1. So the fact that we were able to solve for both s and t, yes? One of them would be enough, granted you didn't make a mistake. Okay? So I'm solving for both of them because I would like you to, after finding s, right? So after finding s, it would be enough to say, okay, now I can go to vector equation of line 2, and I can say s is negative 2. Can you see that when you plug in negative 2 for s, you would have 4 minus 6, negative 2, and 3 plus 4, 7. But I want to make sure that I did it right, so when I solved for t and got t is equal to 1, can you see that when you plug in 1 for t, you also get -2 and 7. So it's just a good way of checking that and making sure. And finally, we have that the two lines are exactly the same. Not only are they parallel, but they intersect at an infinite amount of points. So again, we'll use our parametric equations, but this time when you solve, your variables all go away, and you get a true statement. 5 is equal to 5. Good to know. So again, here, I can already see, by looking at the direction vectors, these two lines are parallel. They've got the 3, 2, and the 6, 4, just like our first example. One is a multiple of 2 of the other one. They're going in the same direction. Okay? From here, we can write our parametric equations. From the first equation, x would be 1 plus 3t, and y would be 2 plus 2t. And our second equation, x would be 7 plus 6s, and the y coordinates would be 6 plus 4s. This creates our system of equations. So we have 1 plus 3t equals 7 plus 6s, and 2 plus 2t is equal to 6 plus 4s. Again, I'll call this equation 1 and this equation 2. So just like before, if I wanted to solve for this to find out if they intersected, I would solve this system of equations. I would probably take equation 1 and multiply it by -2. That would give me -2 minus 6t equals -14 minus 12s. And equation 2, I'd multiply it by 3. And here, initially, I'm thinking I just want to cancel out my t's. So my goal was to get my coefficients in front of t the same. And now when I add, I'm going to get 4. T's cancel out on this side. I get 4, and my s's cancel out. And I get a statement that 4 is equal to 4. Wow, we have all these different things that are equal, right?
Does that mean that 4 is equal to -4 and equal to 2?
No. But that is a good attempt at bad logic.
What's a bad attempt at good logic?
No. So they're the same line, and we are set. Now, these are two-dimensional questions. In 3 dimensions, you can have two lines that are not parallel, but never intersect. These are called skew lines. So they're non-parallel and never intersect. How does this look, and how can we solve this? Well, this is still a two-dimensional one. Should we skip this one? Yeah. Next one is two-dimensional. Let's skip this one too. Let's go to a three-dimensional one and find out, do these intersect or are they skew? They could still be parallel as well. But I hope you can see by the direction vectors that you can't have a multiple of one of the other one. For example, if I wanted the x's to be the same, I could multiply this direction vector by 2, but then my y's and z's would not be the same. So I can already tell that these two vectors are not parallel. But I can't tell if they intersect or if they're skew. Again, anytime you want to find, yes, question? Oh. And they're not bolded. Yeah, it's problematic. So if we go to our parametric equations of the first one, our x would be 2 plus t, our y would be 1 minus t, and our z would just equal t. Our second set of equations, our x would be 3 plus 2s, our y would be 3s, and our z would be negative 1 minus s. Each of these can be equated, and you will get that 2 plus t is equal to 3 plus 2s. Call that equation 1. You will get 1 minus t is equal to 3s. I'll call that equation 2. And you will get that t is equal to negative 1 minus s. I'll call that equation 3. So you have three equations with only two unknowns. In order to solve a system of equations with two unknowns, you only need two equations. Does it matter which two you choose? No. So let's say I look right away, I see equation 1 and 2, if I add them, things will cancel out nicely. Can you see that? Okay. So I'm going to say, I'm going to take equation 1, which is 2 plus t equals 3 plus 2s, and equation 2, which is 1 minus t, equals 3s. I'm going to add them together, so I would get 3 equals 3 plus 5s, and then 0 equals 5s, so s is equal to 0. You could substitute as well. So it doesn't matter which two equations. Now, if I used equation 1 and equation 2, and I found s with equation 1 and 2, I now need to find t with equation 1 and 2. And I can do that by just plugging in s. And you will get that t is equal to 1. So s is equal to 0 and t is equal to 1 was solved using equation 1 and 2. Does it work with equation 3? When I plug in 0 for s, is t equal to negative 1? I mean, t equal to positive 1? No. If it worked in equation 3 as well, then you would get your intersection point. And you could find your intersection point by plugging in 0 for s. If I plug in 0 for s, do you see that I get I get 2, I get 3, I get 0, and I get -1. When t is equal to 1, can you see that I get 3, I get 0, but I get +1? And it makes sense that the x and the y are the same because I used equation 1 and 2 to solve for s and t. But in order for them to intersect, the z coordinate would also have to be the same. So we can make a statement at the end of this one. That these are skew lines. Skew lines means two lines not parallel but never intersect in 3 dimensions.